video 4. Now we're going to switch up gears and we're going to go away from proportions and now see how all of this stuff works for the difference between two sample means. So number one, this is all old stuff from chapter 7, okay? And a lot of our conditions are still going to apply that we had for means before. So the shape of a sampling distribution of just sample means. So again, if we, I don't know, if we, what could we do here? Let's say we take a random sample of 100 students and we calculate what is their mean height. And then let's say a lot of you go out and randomly select 100 students and calculate their mean height. Every one of us would have potentially here, this is probably more than likely going to be true, all of us are going to have different sample means for our 100 people we randomly selected. So if we were to take all of those sample means and we started to graph them together on the same axes, what we would find is it would make a nice normal curve if certain conditions are met here. Number one, if the population is already known to be normal, then hey, we're good. That's the only condition we have to check. If our sample size is big enough by 30 or more, then hey, we can finally use that central limit theorem. What happens if we have a small sample size? Then that's where we had to kind of graph our data and take a look at it to see if the box plot showed any outliers or strong skewness. The mean of all of the sample means we would come up with is basically the population mean for everybody. And our mean of our sample means is an unbiased estimator for the population mean itself. These are basically going to be equal to each other. The standard deviation, our sigma sub x bar, is sigma over the square root of n. Okay, and we can do this, we can calculate this only if this population condition was met. Okay, if the independent condition was met. And we said if we didn't know what sigma was, then we could replace it with the sample standard deviation, or SX in the calculator, which is usually going to be the case. Typically, this will end up being S over the square root of n. But just in case it is known, then you can use it. Here's what all this is going to look like now for the difference of two sample means. We're still going to be hoping to deal with an approximately normal distribution. If both samples come from populations that are both normal, or if both sample sizes are sufficiently large enough, then the central limit theorem will apply to both cases. The mean of all the difference of our means is essentially just the difference of the population means themselves. So this is an unbiased estimator for this, because they are essentially equal to each other. And our standard deviation formula looks a little bit different. Before, if you remember, it was just sigma over square root of n. But now notice the sigma goes underneath the square root. And if it goes underneath the square root, to counterbalance that square rooting of it, we square it. Okay, so this is really saying the first standard deviation, take that value and square it. The second standard deviation, and square it. So it's kind of, I think, a little bit difficult here because we now have subscripts with exponents, which are technically superscripts. So it's a little difficult to see, what's really going on here. So this is our kind of combined standard deviation. We're going to take the square root of really the kind of the variance divided by the sample size plus the other variance divided by its sample size. Okay, and we can only use this formula if the independent condition has been met for both populations, for both samples. And again, if sigma is unknown, pop in the sample standard deviation S. So here's the example we're going to look at. A potato chip manufacturer buys potatoes from two different suppliers, Riderwood Farms and Cammerly Incorporated. The weights of potatoes from Riderwood Farms are approximately normally distributed with a mean of 175 grams and a standard deviation of 25 grams. The weights of potatoes from Cammerly are approximately normally distributed with a mean of 180 grams and a standard deviation of 30 grams. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and weigh them. They are surprised when the average weight of the potatoes in the sample from Riderwood Farms is higher than the average weight of potatoes in the sample from Cammerley. Okay? And that should make sense that they would be surprised because the mean weight from the Riderwood Farms is less than the weight from Cammerley. So if they find that this number, which isn't always going to be 175, but if they took a random sample of 20 potatoes and found that its mean weight is more than the other one, then they're kind of shocked. They don't really suspect that would happen. So the weights are normally distributed, and here's our mean and standard deviation for Riderwoods, and here's for Cammerley. So I just kind of kept the main information from the main problem here. Part A, we're going to describe the shape, center, and spread for the sampling distribution when we subtract our sample means. Okay, and I'm doing Cammerley minus Riderwood Farms. And can you realize why I'm taking Cammerley minus Riderwood? Because Cammerley numbers are larger than the Riderwood ones. And I want to end up with some positive differences here. That's the only reason why I'm subtracting Cammerley and then Riderwood. You can do it the other way. That is perfectly fine. You're just going to end up with negative differences, which is absolutely normal. You can do that. But typically, I'm assuming most of you want to deal with some positive differences here. Now, the shape will be approximately normal. Why will it be approximately normal? Well, we only have 20 potatoes from each shipment. That's not big enough for the central limit theorem. But oh, the population, it said, is approximately normal, and Cammerley is approximately normal. So we're good. We don't have to do anything special here. The center. Now, if we were to take many random samples of 20 potatoes from each shipment, calculate a sample mean from both, and subtract them, and do that over and over and over and over again. And then we wanted to find the mean of all of these differences of our sample means. Well, that should just be equal to the difference of the population means themselves, which are just our 180 and our 175. So we would expect a difference of 5 grams each time we take a random sample of 20 potatoes from each shipment. Now, are we always going to get a difference of 5? No. But in the long run, we should expect a difference of 5. Or if we took the mean of all these mini samples of 20, that we should get 5 in the middle. Standard deviation, we're going to use this formula. Okay? Do we know what the population standard deviation is? We do. It's the 25 and the 30 here. So we take 30 squared. Remember, we have to take the variance technically now, divided by 20, and 25 squared over 20. And when we take the square root of that, I get a standard deviation that's about 8.732. So some of you might be noticing, oh, your standard deviation, it's larger than the mean. Is that okay? Yeah, that's quite all right. That can happen. It doesn't happen often, but it's certainly plausible. Part B, calculate the probability that the mean weight of the Riderwood Farm sample is larger than the mean weight of the Cammerley sample, should the inspector have been surprised. Now remember, let's jump back to here. We mentioned earlier that they are surprised when the average weight of the potatoes in the sample from Riderwood Farms, our X bar sub R here, is higher than the average weight of the potatoes from Cammerley, the X bar sub C. So that's exactly what I'm saying here. Let's calculate the probability that the sample mean from the Riderwood is greater than, I kind of wrote this backwards here and you'll see why. Typically you think, well, shouldn't you have written that as, the sample mean of the Rider is greater than the sample mean from the Cammerley? I mean, that's how you're saying it up here, so wouldn't this be how you write it? You certainly can. But let me talk about why I wrote it this way instead. Everything we've done so far has been Cammerley minus Riderwood. Cammerley minus Riderwood. So in my probability, I need to see Cammerley minus Riderwood. So if I'm saying these are the larger values, this is what I want to figure out. When these values are larger than these numbers. Well, if I subtract the sample mean over to the other side, now this ends up being 0. So really I'm saying if I were to subtract Cammerly numbers and Riderwood numbers, and I'm saying these are larger, then I should suspect negative differences here. Hopefully you guys catch that there. If not, ask me more the next day in class. Now I could have, as I mentioned earlier, if I had written it like this instead, I could have still subtracted this over to the other side, no problem. This ends up being, what's the probability that 0 is greater than the difference this way? And really, this and this are the same thing. It's just that they've been completely flip-flopped of one another. Okay, so you could write it this way. That's fine. Typically, you see your variable stuff first and then your number thing second. Okay, this way the orders just switch, but it really doesn't matter. So let me pop that back in there. All right, so now, so 0 is my main concern here. So if I think about my normal curve, because we verified this is a normal distribution, the mean is our 5 we mentioned earlier, and 0 would be to the left of it. And with a standard deviation of 8.732, I'm not even one standard deviation away. One standard deviation below the mean would take me at like -2, -3-ish. So 0, I just put right here approximately. And so I want to find when my difference of my sample means is less than 0, so I shade less than 0. So now to do normal CDF, I am, what was I thinking here? I don't know. My lower bound is -infinity all the way up to 0. I have a mean of 5 and a standard deviation of 8.72, and that gives me my p-value, 28.35%. Now, some of you might be wondering, Mr. G, you used normal CDF, but in the last chapter, we used T with TCDF. How come we use normal CDF and not TCDF? Well, here's the main thing. Let me jump back to the original problem. In the original problem, we were given the standard deviation of the population. These two numbers here, the 25 and the 30, represent sigma. Okay, we know the population standard deviation, which means we get to use normal CDF. Now, if they did not give us those population values for sigma, then we have to use S. And if you use S, then you have to use T. So this is one of those rare occurrences where we can use normal CDF because we know the value of sigma. So that's the main thing. No sigma, then you can use normal CDF. No sigma, then that means you're going to use S, and if you use S, you're going to use TCDF in its place. So that's the main difference here. Now, should the inspector be surprised if he gets a sample where the Riderwood sample mean is more than the Cammerly sample mean? No, he really shouldn't, because that's going to happen about 28% of the time. And that's not less than our typical alpha equals 0.05. So no, he shouldn't be too surprised if he gets a sample mean from the Riderwood farms that's larger than the sample mean from the Cammerly farms. So here is your problem I would like you to do and bring to class tomorrow. So you can pause the video, read what's going on here. Basically, same type of problem here as we just did. Now you might be wondering, are we still going to use normal CDF? Well, let's just kind of glance through this problem here real quick. Let's see. So we're dealing with a soda fountain machine here. It's got a mean of 27 ounces and a standard deviation. This is talking about the population. This is referring to the population for apparently the medium setting and for the large setting. So these technically are sigmas here. So you will be allowed to use normal CDF and not TCDF. And I know this is going to be a little bit of a confusion point because later when we get to the actual hypothesis testing part, we're going to take samples and we're going to have to end up using TCDF instead of normal CDF. So don't let these problems get you too much here. Okay. Typically, for the most part in this chapter, we're going to be dealing with confidence intervals and hypothesis testing, which the hypothesis testing will use t-distributions. So that is all for video 4. We will see you at video 5.